Welcome, and thank you for joining us. My name is Dean Lee, and I'm Professor of Physics at the Facility for Rare Isotope Beams, or FRIB. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields and strengthen ties between Michigan State University and the community. Today, we have the pleasure of presenting a public lecture by Professor Tracy Slatyer entitled Searching for Dark Matter with the Universe's Highest Energy Light. Professor Slatyer completed her undergraduate work in physics at Australian National University in 2005 and her doctoral work in physics at Harvard University in 2010 under the direction of Douglas Finkbeiner. Slatyer was a postdoctoral researcher at the Institute for Advanced Study in Princeton University from 2010 to 2013 and joined the Massachusetts Institute of Technology Physics Department as a junior faculty member in 2013. She was promoted to associate professor in 2018 and received tenure in 2019. Professor Slatyer works on particle physics, cosmology, and astrophysics. Her research is motivated by questions of fundamental particle physics, such as the nature and interactions of dark matter. She seeks answers to these questions by studying possible signatures of new physics in astrophysical and cosmological data. Her research includes scenarios where dark matter experiences new forces of nature, precision theoretical predictions for photon signals from heavy colliding dark matter particles, modeling the possible effects of dark matter interactions on the history of the early cosmos, and analysis of high-energy gamma-ray data in search of dark matter signals. She was a co-discoverer of the giant gamma-ray structures known as the Fermi bubbles, erupting from the center of the Milky Way galaxy. If you have any questions during this talk, please type them into the chat or question and answer dialog box. At this time, it is my great pleasure to introduce Professor Slatyer.
Great. Well, thank you very much for the kind introduction and for the invitation to be here. Just to check, can you hear me okay?
Yep.
Okay, great. All right. So yeah, as Professor Lee said, I want to talk to you today about how we might search for dark matter using the universe's highest energy light, i.e. gamma rays. So I want to begin by just talking a little bit about what gamma rays are, what I mean by gamma rays, what I mean by highest energy, and where gamma rays typically come from in our galaxy, because, spoiler, most of it is not dark matter. Then I want to introduce a little bit the dark matter puzzle that motivates a lot of my research. And you talk a little bit about why we might want to look for dark matter in gamma rays, what kinds of things gamma rays could potentially teach us about dark matter and its interactions. And then I want to tell you about some examples of how dark matter physics might show up in gamma rays. I want to tell you about this long-standing excess of gamma rays from the galactic center that has been proposed as a possible signal of dark matter particles colliding in the center of our Milky Way galaxy. And how we might try to figure out whether that's actually dark matter or whether it's a different source of gamma rays. I'll tell you a little bit about what the status and prospects are of searching for heavy weakly interacting massive particles more generally with gamma rays, and then give you an example of how gamma rays can also tell us about models of dark matter that have nothing to do with weakly interacting massive particles. All right, so as was already said, if you have questions that need clarification during the talk, feel free to put them in the chat, and Dean will let me know if there's a question that needs answering. All right, so jumping right in. By gamma rays, I just mean high energy light, effectively. So the same light that comes from the sun or from the light bulbs in our rooms, just more energetic by more than a factor of 1,000,000. So this is a nice little diagram that I found online about the various frequencies and wavelengths of light and how we label them. So gamma rays are light with wavelengths smaller than an atomic nucleus. They're very highly energetic. As I said, about 1,000,000+ times more energetic than sunlight. Now, In fact, the gamma rays that I'll be talking about in this talk are mostly a billion or more times the energy of sunlight. A useful unit there is giga electron volts, or GeV. One GeV is about a billion times the energy of visible light. So, where do these things come from? How are they produced? So, generally, they're produced in very energetic, violent processes throughout our cosmos. And as such, they can tell us about those energetic and violent processes when we measure them in our telescopes. So the most common source in our galaxy is from high energy charged particles, which we call cosmic rays, interacting with the interstellar gas and light. So I'll show you a little video picture of that. So the picture here is that out in what we normally call the vacuum of space, there's actually a lot of hydrogen out there, protons. When a high energy proton comes in and strikes a hydrogen atom, it can produce secondary particles called neutral pions. These as well as other particles, charged particles, electrons, and positrons. But the pions decay about 99% of the time directly into gamma rays. So so as a result, when we look out at the sky in gamma rays, a lot of what we see looks like an image of our Milky Way galaxy, but instead of looking how it looks in visible light dominated by the stars, it's dominated by where the gas is and where the cosmic rays are. So let's just say a little bit about our galaxy first. We live inside the Milky Way. The Milky Way is a spiral galaxy. This is a artist's impression of what it would look like from the top down. So it's got this sort of bulge region in the middle and then these spiral arms extending out. If you were to look at it side on, which is close to what our usual view is like, you would see this sort of bulge of stars in the middle, this disk surrounding it, and then this faint and diffuse halo of stars around the disk. And we are in one of these spiral arms around 25,000 light years out from the center. So when we look up at the sky, we see basically a band of stars. And if you've been in the southern hemisphere, you can see the center of the galaxy more clearly. This band of stars across the sky, which is called the Milky Way, corresponds to looking essentially edge on at our galaxy. I'm originally from Australia. This is a time-lapse photograph of the Milky Way taken from a point in Australia where you see this beautiful band of stars and dust. That's our galaxy. So what does it look like if we look at it in gamma rays instead, if we could see with eyes that can see this very high energy radiation? From the argument that I just gave you, you should expect it to look more or less like the distribution of gas in the galaxy weighted by the cosmic rays. So what does that look like? So if we were to take this image of the Milky Way, but take an image of the whole sky and rotate it so that the disk of the galaxy is is this horizontal band in the center of the image, if we could just see the gas in the galaxy, it would look something like this. So this line here is the plane of the Milky Way. This is the center. You can see that there's a lot of dust and gas in this central band of the galaxy, but then there are these additional, quite structured gas clouds and gas filaments extending above and below the galactic plane. And when we look at the sky in gamma rays, indeed, we see that it looks a lot like this. So this is an image of the gamma ray sky taken by the Fermi Gamma Ray Space Telescope, which launched in 2008 and has been up there in orbit taking data for the last 16 years. So it looks more or less like what we expected. There is this band of bright emission across the galaxy. So this tells us, we understand what's going on. We're correct about this. High energy charged particles interacting with the gas and starlight produce most of this emission. But there are some other things in this image. So first, this sort of conventional emission is interesting to study on its own. It tells us about the properties of our galaxy. But I am more interested in the other stuff that is in this image that we may not fully understand yet. So what other things are there in this image? So first, you can see these bright spots through the sky. These are mostly not associated with the gas and dust. We call them point sources of gamma rays. That's just a descriptive term. It means like they look like individual points rather than some extended structure like the gas. So what are those point sources? They can be gamma ray emitting stars. Pulsars spinning neutron stars can produce high energy gamma rays. When stars explode, going supernova, afterwards, there is often a supernova remnant left that continues to glow in gamma rays for a long time. So some of these dots are supernova remnants. Some of them are also in other galaxies. We live inside the Milky Way, and so when we look at the sky, it's kind of the first and brightest and closest thing that we see. But in other galaxies, there can be, again, very high energetic violent events, especially when matter falls onto the supermassive black holes at the center of those galaxies. And that can lead to high energy gamma ray emission that is visible from all the way across the universe. So these point sources can include both galactic and extragalactic sources. And then you can ask the question, okay, so once you take those away, you take away the emission associated with the gas and dust, and you take away the emission associated with the point sources, what else could be hidden in this image? And one of the things that could be hidden in this image is a possible signal from dark matter. So let's talk a little bit about that puzzle. Now, if I wanted to give a talk just about the evidence for dark matter, I could very easily spend the whole hour on that. I also know that if you've been following this lecture series, you've heard other people give the talk about why we think the dark matter exists and what the evidence base is for it. So I'm really happy to answer questions about it, but you guys are going to get the 1 or 2 slide version of that talk. And then we'll go back to talking about gamma rays. So the puzzle of dark matter is that we have pretty good evidence that roughly 84% of the matter is dark, which means it has no or very tiny electric charge, and it interacts at most very weakly with known particles. There are a bunch of different lines of evidence for that statement, from rotation curves in galaxies, so how fast stars and gas clouds are moving in galaxies, how fast galaxies are moving in galaxy clusters, from looking at gravitational lensing observations of colliding galaxy clusters, from imprints left on the cosmic microwave background radiation that's sometimes called the afterglow of the Big Bang, and even the fact that galaxies exist and look like they look like at all, we believe is based on an invisible cosmic scaffolding built from dark matter. So all this evidence suggests that dark matter, by which again we just mean something that behaves like ordinary matter in terms of its gravity, but doesn't have electromagnetic interactions. All our evidence is that this stuff is pretty pervasive and has been around for a long time, but we have only ever detected it through its gravity. If it has non-gravitational interactions with the particles we know about, that's very possible, but we haven't found those interactions yet. But just by measuring its gravitational footprint and how it's distributed through the universe, we are able to say that there are no good candidates for dark matter within the physics we currently understand. And that makes it one of our biggest clues as to what might lie beyond that known physics. So, faced with a puzzle like this, what do particle physicists do? We come up with hypotheses for what the underlying fundamental nature of the dark matter might be. And this is usually what people mean when they talk about discovering dark matter. In some sense, we've already discovered dark matter. You know, we can map out where it is in the universe through its gravitational pull pretty accurately. We think we know quite a bit about its properties and how it behaves, but we don't understand what this matter is, where it comes from, how it was formed, what interactions it has, is any, how to describe it in terms of particles. If it even has a description in terms of particles, it might not. And so understanding those questions is what people usually mean when they talk about discovery of dark matter as a goal. So, what has the particle physics community done with this grand challenge? We have come up with a lot of plausible explanations for what this stuff could be. I do not want you to understand everything. I do not want you to try to read everything on this slide. It's a busy slide. It was created by one of my colleagues, Tim Tate, as part of a community planning process called Snowmass back in 2013. We've done a more recent one in 2022. I'll show some plots from that later in the talk, but this is still a reasonably good summary of the situation. So there are just a few things I want you to take away from this slide. The idea of this slide is that everything within the red region is a class of possible scenarios for what dark matter could be. Not even a single possibility for what dark matter could be, a general category of possibilities. Everything outside the red region is a broader idea for how physics might be extended beyond the standard model of particle physics that could possibly connect to dark matter. So, for example, dark matter could be related to new symmetries of the universe, such as supersymmetry, or extra dimensions beyond the 3 space dimensions and 1 time dimension we're familiar with. It could be related to puzzles of the Higgs sector in the Standard Model, or of the strong interactions where there are ongoing things that we still don't understand and results, experimental results that seem very surprising from a theoretical perspective. Or it could have something to do with the neutrino sector of the Standard Model. In a sense, neutrinos are dark matter since they are matter that gravitates but doesn't have electromagnetic interactions. We just know, unfortunately, that they're not abundant enough to be more than about 1% of the dark matter. So dark matter could also involve new forces. And as you heard in the introduction, I've worked on this a little bit, beyond the forces of nature that we already know about, in the same way that ordinary matter feels electromagnetism and dark matter does not seem to. Dark matter could be our first clue, our key to a whole new sector of particles and interactions outside the Standard Model. So those are all, so dark matter is, by the fact that we can't explain it, potentially a big clue to what we might be missing, and understanding it, as well as being valuable in its own right, just to understand what 84% of the matter in the universe is, it could potentially serve as a key to unlock other puzzles of fundamental physics. So that's the positive point. The less positive point is, so you can see that the issue is not that we lack ideas for what dark matter could be. That is not the problem here. The problem is, at the moment, the vast majority of these scenarios are pretty indistinguishable from each other experimentally because all of them predict that, all of them are consistent with the data in that all of them predict that dark matter gravitates, and all of them are consistent with dark matter having weak enough interactions that we would not yet have detected it. And while there are ongoing efforts to better measure how dark matter is distributed through its gravitational footprint, for a lot of these scenarios, you expect that not to be very good at distinguishing these scenarios from each other. They will all have very similar distributions and very similar gravitational footprints as a result. So that has motivated me and many, many, many other people, this is not just my individual research, to try to look for ways that we might distinguish these scenarios from each other, especially through their non-gravitational interactions. We don't know if those non-gravitational interactions exist, but in many, we don't have direct observational evidence of them as yet. But in many of these scenarios do predict such interactions. If they exist, we can go look for them. If we were to positively identify one of them, it would be extremely powerful in eliminating hypotheses. All right, so what do I mean by non-gravitational interactions of dark matter? Basically, I mean any process through which a dark matter particle can interact with the known particles, can exchange energy or momentum into them, can convert into them under some circumstances. So a classic example of a dark matter interaction with the ordinary particles would be dark matter annihilation. So this occurs in many, but not all, of the theories on the previous slide. And the idea is that it might be possible for dark matter particles to collide with each other and produce known particles, which I am going to label by SM here. DM means dark matter, SM means Standard Model of particle physics. So the picture here is that out in space, two dark matter particles collide. They undergo this interaction that we would like to understand, this new physics, and they produce the particles that we know about in the Standard Model, which could be anything. These could be Higgs bosons or W and Z bosons, quarks and antiquarks, electrons, muons, tau leptons, and so on. Now, most of those particles are, now on one hand, that seems like a lot of possibilities, but most of those particles are unstable. So if they are produced, they will promptly they'll promptly decay into stable known particles. And that's a much smaller set of possibilities. The stable known fundamental particles, we have electrons, positrons, protons, antiprotons, nuclei and antinuclei, but those are heavier and tend to be produced more rarely. Neutrinos and photons. And that's basically it. So what this annihilation process would look like observationally is that in regions where there's a lot of dark matter, there are these additional particles apparently popping out of nowhere. And we can search for all of these particles, but in the talk today, we're going to focus on the photons. Now, in principle, you could see photons at all different kinds of energies from a process like this, But the energy scale of the particles produced by annihilation is set by the mass energy of the dark matter. Einstein told us E equals mc squared. This annihilation process converts the mass of the dark matter into the energy of visible particles. So if the mass of the dark matter is sufficiently heavy, the energy that it's released when it's annihilates will mean that the photons are typically in the gamma ray energy range. And by heavy enough, what I mean here is if the dark matter is heavier than an electron, which is one of the lightest fundamental particles that we know about. Actually, even somewhat lighter than an electron would still qualify as gamma rays. But if the dark matter is as massive as an electron or heavier, which holds true for all particles in the standard model except neutrinos, then the typical photons you would expect from this process will be in the gamma ray energy range. There's another interesting thing about annihilation. So in the class of all models that have dark matter annihilation, there is a subclass in which dark matter annihilation is actually what sets the amount of dark matter in the universe today. The idea here is that we had much more dark matter early on, and then most of it annihilated away. In that case, there's a direct connection between the residual amount of dark matter remaining and the rate of this kind of process. We've measured the amount of dark matter in the universe, so that means that we know what the rate of this process should have been, at least in the early universe. And if the underlying particle physics of that process is the same today as it was in the early universe, that means that we have a prediction for what kind of signal we should get in gamma rays. Okay, so that sounds cool. So what would we have to do to look for dark matter annihilation signals in the sky? Well, one concern you're always going to have is, well, we know that this is not the only source of gamma rays. We've looked at the gamma ray sky. We've seen that there's evidently a lot of gamma ray emission coming from stars and from interstellar gas. So how do we tell them apart? Well, as I said, this annihilation signal should be most important in regions where there's a lot of dark matter, a high dark matter density. So one important thing to know is how the dark matter is distributed through our galaxy. One of the early pieces of evidence for dark matter was by Vera Rubin and her collaborators, who, when they tried to measure the rotation speed of stars and gas clouds in galaxies, and you can use the velocity of stars and gas clouds to try to map out the gravitational potential of a galaxy. So down here, I'm showing a little cartoon where the yellow blobs sort of represent the bright central region of that galaxy, that bulge in the inner spiral arms that we talked about before. And these dots represent stars and gas clouds orbiting in the outskirts of that galaxy around that bright inner region, just like planets going around the sun. Now, if this left-hand panel is showing what you would expect, if the only matter in the galaxy was what we could see in this bright inner region, if you're familiar with the solar system, you know that the more distant planets orbit around the sun more slowly. And so here, similarly, you would expect that as you go further out from this bright region, the stars and gas clouds would be orbiting more slowly. But in fact, that's not what we see. The orbital speed remains almost constant out to large distances from this bright inner region. So that could suggest a couple of things. One suggestion was maybe this reflects a modification of gravity on galactic scales. But we have, I think we have pretty good evidence that that is not what's going on. Under the dark matter hypothesis, the increased speed of these particles at large distances does reflect that the gravitational field is stronger out there than you would have expected. But the reason it's stronger out there is because there is extra matter, not just in this central bright region, but extra invisible matter, the dark matter, in the outskirts of the galaxy as well. So from observations like this, you infer that surrounding the spiral galaxy that we can see is this broad, extended dark matter halo. It's still most dense in the center, just because gravity causes the dark matter density to be higher. In the set, dark matter tends to fall towards regions of high gravitational field, the same as ordinary matter does. But the halo extends out a long way, and it's also much more spherical than the spiral galaxy embedded in its core. So we would expect a dark matter annihilation to have this property. It should be brightest at the galactic center, falling off away from the galactic center, but look more spherical than the galactic disk. So that's one tool that we can use to try to distinguish a dark matter annihilation signal from something else. We can look for dark matter that should have a roughly spherical distribution following the dark matter halo. And we have some expectation for how fast it should rise towards the center, although there are large error bars on that expectation. The other thing that you can do when you're looking for a dark matter annihilation signal is try to use information on the energy distribution of the signal. So this upper plot is showing what you would predict for the energy of the photons produced by dark matter for a particular dark matter mass, which is about 30 GeV. This corresponds to about 30 times the mass of a proton. Um, so the y-axis here is the amount of photons, the amount of power in photons per logarithmic interval in energy, and the x-axis is the energy of the photons in those GeV units I mentioned earlier. Remember, 1 GeV is about a billion times the energy of the light from our light bulbs or from this screen. And these different lines correspond to annihilation into different standard model particles. So different kinds of quarks, tau leptons, electrons, and positrons. So again, you don't need to remember the details of like this plot and which line corresponds to which standard model final state. What I want you to take away from this is that all of these cases, this energy distribution basically looks like a bump. The position of the bump is fixed by some overall mass scale that's mostly determined by the mass of the dark matter. As we said earlier, E equals mc squared. When we say the dark matter mass is 30 GeV, we really mean 30 GeV divided by c squared. So the scale is set mostly by the mass of the dark matter and secondarily by what standard model particles it annihilates to. The general shape is a bump, goes down at low energies, goes up at high energies, peak in the center. And the overall normalization of this signal is going to be determined by the annihilation rate. All right, so ways that we can look for a dark matter signal are to look at its spatial distribution and look at the energy distribution. So I mentioned to you before the Fermi Gamma Ray Space Telescope. So what happened when we looked at the first data from the Fermi Gamma Ray Space Telescope when we looked at the gamma ray sky? And this is a little artist's impression of the Fermi Gamma Ray Space Telescope up here. So, and these initial studies were done in 2009, a year after the telescope launch. So this is a long-standing signal at this point. So, what we see when we look at the overall data, this is a zoom in on the region around the center of our galaxy where you would expect the dark matter density to be highest, but also there's a lot of gas and a lot of dust, and so the backgrounds are also largest. On the left-hand panel, you see this emission along the galactic disk. So red means more emission, green means, so the scale of emission goes from red to green to blue to purple here. If you then try to subtract off an estimate for how much emission should there be just from the dust and gas that we know in this region, then you get the right-hand panel. And so what you see in the right-hand panel is that you've subtracted most of the emission along the plane of the Milky Way galaxy, and you're left with just this blob in the center. Now that blob of gamma ray emissions, sorry, you can't see it that well in this image, but I will tell you it is a lot more spherical than the disk of the Milky Way. It's not extended along the plane in the way that the disk is. Now, these different plots correspond to 3 different energy bands, so low energies, medium energies, and high energies. And you can see it a little by eye, but you can make this more quantitative that the blob is biggest in the middle energy range. So it has a broad peak-like spectrum. It falls at low energies and also falls at high energies. So that general structure is what we might expect from dark matter. It's pretty steeply peaked at the center of the galaxy, but it extends out at least 10 degrees from the galactic center, which corresponds to a physical scale of about 5,000 light years, and it looks roughly spherical over that range. And furthermore, the brightness of this signal is, when you work it out, is just about what you would expect from dark matter models where it was the annihilation rate in the early universe that fixed the amount of dark matter today. So when we and others saw this back in, this was sort of worked out from 2009 to 2014, we were very excited. Like maybe this is the discovery of dark matter annihilation. Maybe we're learning that dark matter annihilates efficiently into quarks that subsequently decay into gamma rays. But you may have noticed that I said this was worked out in 2009 to 2014. And I'm not telling you the story of how we discovered dark matter in gamma rays. And the reason for that is because there are other plausible explanations for what this blob of gamma ray emission could be. In particular, told you earlier, we know about stars that emit lots of gamma rays in the right energy range. Now, we think this is probably something coming from within our galaxy, not from another galaxy, because it's at the galactic center. So I told you that the gamma ray emitting sources in our galaxy were mostly pulsars and supernova eminence. And pulsars in particular emit lots of gamma rays in the right energy range and with pretty much the right energy distribution to match this signal. So pulsars and in particular, there's a class of pulsars that seem to match the data pretty well in terms of energy distribution called millisecond pulsars. This is an artist's impression of a millisecond pulsar. One reason that so millisecond pulsars are pulsars that rotate about 1,000 times a second. Pulsars are neutron stars. They're composed of ultra-dense neutron matter. As they spin, they emit a beam of radiation, which can extend to the gamma rays, but also to lower energies. And one way to produce millisecond pulsars is if the pulsar is orbiting around another star. When the other star reaches its red giant stage, the pulsar can absorb the matter from that star onto it, and that can spin up its rotation to high rates, which was what produces these millisecond pulsars that rotate about 1 time per millisecond. Now, if that's the production mechanism, you would expect these pulsars to be more abundant in cases where there are a lot of stars so that they can form these two-body systems. But so if that's the case, then you would expect the signal from such pulsars to get brighter and brighter towards the galactic center where the density of stars is higher. So that could potentially match the signal distribution pretty well. So how would we tell these apart? Well, there are a few things that you might do. If we were talking about, say, 10 pulsars making up the whole excess, this would be a very easy problem, and we would have solved it already because we could just see that the excess doesn't look like a fuzzy blob, it looks like 10 individual stars. Unfortunately, what we know at this point, so I and others have done a lot of work in trying to understand where the galactic center excess is made of point sources. And the tentative conclusion, as far as I can tell, is it's consistent with being something smooth and diffuse. It's also consistent with being 10,000 plus faint point sources. So provided that you're okay with having 10,000 pulsars in the inner galaxy that we didn't know about previously, which would be exciting and interesting, but certainly isn't impossible, then it doesn't seem like we're going to be able to distinguish the pulsar and dark matter signals by that mechanism. It looks pretty consistent with either something like dark matter annihilation or a large number of faint point sources. But maybe we can do something just by looking at the shape of the signals. We said before the dark matter signal should be roughly spherical, like the halo. What about the pulsar distribution? Well, that's more uncertain, and it depends on exactly what kind of pulsars you're looking at and how they're formed. For example, do they need to be in a system with another star in order to produce this emission? But it's plausible that you might expect it to resemble the Milky Way's stellar bulge, since that's where there's a large population of stars that are pretty old. They're different from what you see from stars you see elsewhere in the galaxy. So it might make sense that they have a special pulsar population associated with them. Unfortunately, the problem here is that this bulge is also pretty spherical. And so distinguishing the bulge from a spherical distribution requires looking at the details. Now, just as a side note, there's another striking feature in the sky for which this shape-based analysis was really successful that my collaborators and I found in 2009 looking at the early Fermi data. So this is this figure-8 shape in the center of this image shown in gold and red here. So those structures are called the Fermi bubbles. And when we very first saw those structures, it looked like a fuzzy blob, and we were like, maybe it's dark matter. But then as soon as we got better data and we were able to see this figure-8 shape show up, we were able to say, okay, no, whatever that is, it is definitely not dark matter. It does not look like this dark matter halo. So in that case, the shape argument was very successful and very easy. We were able to separate the possibilities well. But that was because this figure-8 shape was so different from the expectations of a dark matter halo. The stellar bulge is a lot closer. So what happens? But you can take these two shapes and compare them to the data and ask which does better. So this is the classic approach, is to fit the data as a combination of your best estimate of the backgrounds from the known sources of gamma rays in the galaxy, in particular from charged particles interacting with the gas, and also put in a model for a spherical profile versus the bulge and ask which one does better. Unfortunately, it turns out that these are similar enough that which one does better depends on the details of how you model those gamma ray backgrounds, so how you model where the gas and where the cosmic rays are in the galaxy. And that's somewhat difficult because we can't send a spaceship out to just measure the gas density and the cosmic ray density at every point in the galaxy. Unfortunately, we have to work by inferences from observations at other frequencies. So this is a significant ongoing controversy and problem. I'll just mention that my colleagues and I recently put out a nice paper led by Ed Ramirez of Rutgers, who just defended his PhD thesis this past week, where we addressed a different aspect of this question, which is maybe we're missing something by just asking which fits better, a stellar bulge profile or a spherical profile. Maybe the galactic center excess has features that don't really look like either of them. So we set up this pipeline to extract the signal shape directly from the data using a very flexible signal model. The method is called Gaussian process modeling, which I can say more about if people are interested. And so these plots on the right-hand side are showing again like zoom-ins of the galactic center, and they're showing the data-driven profile that we extracted for the galactic center excess using 3 different background models. And the first one is actually using a linear combination of all the background models that people have proposed in the literature. And you see that in all cases, we see this bright blob at the galactic center. But then what happens as you move away from the galactic center is the emission does get fainter in all these cases, but how it gets fainter is pretty different. In this particular background model, the emission falls off very slowly. There's still a lot of galactic center excess at the outskirts of this region, whereas in these first and third background models, it falls off much faster generally. But also in these first and third background models, you see extra features like this sort of arm extending out from the excess. Now, that could be just that there's a feature in the gas there that none of our background models are properly capturing. This initial study just used a single energy bin. We do want to extend this to use energy information, which would be the other key tool for distinguishing what's in this galactic center excess from what could just be in backgrounds that we're not getting quite right. But so we hope this will be a useful tool for trying to disentangle the two. But my zeroth order situation here is that the differences between a spherical profile and the bulge profile are mostly in these outskirts, and the outskirts depend a lot on how you model the background. So where next for this particular excess? Looking gamma rays at the galactic center, the uncertainty in backgrounds makes it hard to nail down the shape. So one way to proceed is to try to understand the backgrounds better and to make sure that we're using as much of the data as we possibly can to distinguish backgrounds from signal. Another possibility is just to try to avoid the backgrounds. Future gamma ray telescopes could look at the dwarf satellite galaxies of the Milky Way. This has already been done with Fermi, but so the Milky Way is surrounded by smaller galaxies orbiting it. Those little galaxies should be rich in dark matter, but they should have much less in the way of pulsars or other gamma ray backgrounds. Unfortunately, the current sensitivity of Fermi is not quite good enough to be able to test the dark matter hypothesis from looking at those dwarf galaxies, but future telescopes with better sensitivity could potentially either confirm or rule out a dark matter interpretation for the excess based on such observations. The other possibility is to look in other frequencies. We said before, if dark matter annihilates, it probably produces particles other than photons, such as electrons, positrons, protons, antiprotons, neutrinos, and so on. We can look for those with other telescopes and are looking for those with other telescopes. For pulsars, you also expect there to be multi-wavelength counterparts. That beam of radiation that they put out typically is bright in radio and X-ray, as well as in gamma rays. And there are current radio and X-ray telescopes scanning the galactic center region looking for pulsars there. We found, I believe, the first millisecond pulsar in the galactic center region just last year. Now, finding one pulsar does not really tell you whether or not there are 10,000 there, but it's a hopeful sign that there might be more discoveries to come. But if you're like me and you think pulsars are great, but really I'm interested in dark matter, you might ask the more general question, okay, so beyond this excess, what can gamma rays tell us about dark matter annihilation? So here we were looking at this very specific energy range of just a few GeV because that's where we saw an excess. But we could also see gamma rays from dark matter annihilation at higher or lower energies. And higher energies in particular, I find pretty interesting. Let me explain why. So I said before that there's this class of models where the annihilation rate directly determines how much dark matter you have today. So we can ask, as a function of the mass of the dark matter, what annihilation rate, or really annihilation cross-section, which is like the rate once you factor out the dark matter density, what annihilation cross-section do we need to get the right amount of dark matter in the universe today? So that's a benchmark, and we can ask, can we test that benchmark? If that cross-section is large enough that we should be able to see a signal if it's occurring, then that means that we can test the hypothesis that this was how we got the abundance of dark matter that we observe. So this plot on the right is showing the cross-section on the y-axis. So again, this is the fundamental parameter that goes into the dark matter annihilation rate. And on the x-axis, we have the dark matter mass in GeV divided by c squared. So previously, we were thinking about dark matter masses. I showed you a plot for dark matter at 30 GeV. To fit the galactic center excess, you sort of want to be in the 50 to 100 GeV range. So this gold line corresponds to the benchmark that you need to get the right relic density. And you can see it's pretty consistent up to pretty high masses. So this cutoff here is about 100,000 GeV. So why does this line cut off at some point? Well, if dark matter is heavier than that, heavier than about 100,000 times the mass of the proton, then this mechanism for making the right amount of dark matter actually breaks down. You find that you just cannot make the dark matter annihilate fast enough to get to the observed abundance in the present day. So there's this finite window in which this mechanism could make the correct amount of dark matter for our universe. Okay, so what else is going on in this plot? This pink region is showing roughly the region that we can test, that we have sensitivity to with current telescopes as a function of the dark matter mass. And you can see that this pink line crosses the orange line around 100 GeV. So what that says is that if dark matter was annihilating with this rate and was lighter than about 100 GeV, we should have seen a signal already. The galactic center excess is consistent with that. To explain it, you need dark matter between about 50 and 100 GeV with a cross-section that's basically on this gold line. So indeed, we should have seen that already. If the galactic center excess is coming from dark matter, we have seen it already. If the galactic center excess is not coming from dark matter, if we could confirm that it's coming from pulsars instead, then we would be able to say, all right, we looked for that, we didn't see it, so we can rule out that possibility. But current telescopes have sensitivity only to dark matter masses, shown by this pink region, have sensitivity to this benchmark only up to about 100 GeV dark matter masses. For the next 3 orders of magnitude, there is a well-defined thermorelic benchmark, but we just don't have the sensitivity to see it yet. But with relatively near-term telescopes, near-term here means about the next decade, we could have sensitivity to pretty much this whole region. So if this is how dark matter was produced in the early universe, I think we have a good chance to find out. So if we're looking for this high mass dark matter, then it means that we're also looking for high energy gamma rays, because the energy of the gamma rays is controlled by the mass of the dark matter via E equals mc squared. And while for GeV gamma rays, you really need a space-based telescope, like the Fermi Gamma Ray Space Telescope, for higher energies, you can actually build gamma ray telescopes on the ground. You're basically using our atmosphere as a detector. When these high-energy gamma rays hit our atmosphere, it produces a flash of lower energy radiation, and we can look for that with these large ground-based gamma ray telescopes. The advantage of being able to go on the ground is you can build really big telescopes. It's hard to launch gigantic telescopes into space. It's very expensive. It's much easier if you can build them on Earth. And this is an artist's impression of what one of these telescope arrays would look like. So the green region on this plot is based on 2 telescopes, one of which is under construction, one of which is proposed, called the Cherenkov Telescope Array, which will have both this is a European project predominantly. It will have both a northern hemisphere side and a southern hemisphere side. The northern hemisphere side already has telescopes there and it's in Spain. In the southern hemisphere side, they're building the infrastructure. And the other one is a US and Mexico project called the Southern Wide Field Gamma Ray Observatory, which is, has development funding from the NSF and which would use a somewhat different technology that would be complementary to the Cherenkov Telescope Array. So this is something to keep an eye on. At the moment, I would say we've only sort of probed part of this possibility for how dark matter could be produced in the early universe, but over the next 10 years, we could have sensitivity to almost all of it. There are other exciting directions, such as looking for antimatter, and in particular, antideuterons and antihelium should be very rare from astrophysical processes. The backgrounds should be essentially zero. We actually have a dedicated experiment that's going to look for antideuterons and antihelium going up from a balloon from Antarctica this summer, this southern summer, so northern winter. And last I looked on the web, it looks like the launch for that is planned for just a couple of weeks away. So that will be very exciting. So you might ask, okay, Tracy, but if I only care somewhat about testing the possibility the dark matter that the dark matter abundance was fixed by annihilation, what kinds of dark matter scenarios can I test with these observations? Well, to me, this is perhaps the cleanest way to test the classic weakly interacting massive particle scenario. So this is a really long-standing idea for dark matter. The dark matter could be WIMPs or weakly interacting massive particles. And in the simplest version of this scenario, what might we mean by weakly interacting is that the dark matter interacts directly with the W and Z bosons, which we call the weak gauge bosons of the standard model. Now, in the classic version of this WIMP scenario, the abundance is determined exactly as we've described by annihilation in the early universe, and we can predict the annihilation rate today. And if dark matter's only interactions are with W and Z bosons, then we can use what we know about the physics of the standard model to classify all the possibilities for dark matter. So if you've I could have I haven't pulled up the specific newspaper headlines here, but if you've been following this story for the last few decades, you may have seen a number of articles saying things like, "Are WIMPs dead?" or, new experiment fails to find WIMPs, or new experiment challenges WIMPs as dark matter. And sometimes people do say the WIMPs are ruled out because we haven't found them yet. But this is not really true, in my view, because if you take these simplest classic WIMP models where the dark matter just interacts with the W and Z bosons, it's a finite range of possibilities, and they essentially have no free parameters. The one free parameter is the mass of the dark matter, but you can ask, what dark matter mass do I need to get the right amount of dark matter in the present day universe to be on that benchmark annihilation cross-section curve? And that has a well-defined answer for each of these discrete possibilities. This plot on the right is showing how each of those possibilities would show up in a direct detection experiment. This is strictly only showing about half the possibilities, but I can tell you that the other half is actually even more pessimistic from the perspective of direct detection. So the y-axis here is showing the relevant cross-section that these models have in big underground direct detection experiments. So these are looking for dark matter particles coming in, bouncing off the ordinary matter, and causing it to recoil. These green lines up the top were the constraints from these experiments at the time that this paper was written a couple of years ago. This dashed line is the sensitivity of the best current experiments that we have for dark matter that are currently running. When they get to the end of their lifetime, they'll have a sensitivity about here. These red and blue points are showing these predicted signals for these very simple classic WIMP models. So, and you just see that we haven't tested any of these yet with direct detection. They all predict signals too small to be seen at this experiment. The y-axis is the mass for these scenarios. Units here are TeV. A TeV is 1,000 GeV. So these are about 2,000 to a few 100,000 times the mass of a proton. So GeV divided by c squared is about the mass of a proton. This gray region here is the region in which we would start to have neutrinos becoming an unshieldable background in these experiments. So we could potentially test these models with direct detection. This dotted line here is an idea for a future direct detection experiment, so the next generation direct detection experiment. So that would be a way to probe these models, but it's just wrong to say that we've ruled them out already. We don't know. Like, these are simple possibilities and they're completely viable. But because they all got their abundance through annihilation in the early universe, they all predict they all predict a minimal annihilation rate in the present day, and thus they all predict a gamma ray signal that we can look for with experiments like with telescopes like the ones proposed here. And my collaborators and I have some work in progress, but I think all indications is that if those telescopes perform up to expectations, they should be able to test essentially all of these scenarios. So if you just want your sort of like general way to test WIMP dark matter, then I think this is a very promising direction. I'm really looking forward to seeing the results. Okay. Now, of course, dark matter doesn't have to be a WIMP, and it doesn't have to annihilate. Told you earlier, there are tons of different possibilities for dark matter. So I wanted to give you just one example of what that could look like, but there are many others. As an example that I'm not going to talk about, dark matter could be tiny black holes left over from the early universe, in which case their slow evaporation could produce gamma rays. There are other scenarios where even if dark matter is really, really, really light, even if its mass is far below even that of neutrinos, it could leave imprints in gamma rays. Well, how does that happen? Well, in some scenarios, sufficiently light dark matter particles can convert into light and vice versa in the presence of electric and magnetic fields. So here previously we talked about dark matter particles colliding, but here it would just be you have one dark matter particle coming in, and then in the presence of an external field, occasionally it converts into light, or vice versa. Now, and the classic models that have this behavior are called axions and axion-like particles. So you might ask, can we see the effects of such interconversions by looking at light? The answer is yes. There's a wide range of possibilities to do it. What can you do with gamma rays in particular? So with an MIT PhD student, Shuyuan Zhang, and a postdoc He we recently looked at the question of what you might be able to do with gamma ray polarization. So this is the same kind of polarization as we talk about with polarized sunglasses. I think this is the first time I had to pull slides from the American Academy of Ophthalmology website. So when light travels to us, it can oscillate along two different directions, perpendicular to its direction of motion. And the way that polarized sunglasses work is that they absorb one and only one of those directions. So how is this relevant to new particles? Well, if light can oscillate into new particles, which might or might not be the dark matter in a magnetic field, then typically only one polarization of light can oscillate depending on the magnetic field. So in this sense, there is some probability for light to get absorbed into this new channel, into conversion into this new particle, but only if it has a particular polarization. So a region of space containing a magnetic field then acts kind of like polarized sunglasses, that there is absorption of light, but only in a specific polarization direction. This is just, if you look to background through polarizing lenses or not through polarizing lenses, you can see visually the difference between blocking or not blocking this light. Now, unfortunately, when we usually can't choose to say, look at a region of space that has no magnetic field, that's usually not an option. So instead, what we need to do to look for this kind of effect is to see a detector that can measure polarization. And this has been done at lower frequencies for a long time, but what we looked at is whether you could do it in gamma rays. And one possibility for that is the AMSO2 detector, which is up on the International Space Station. It was actually launched on the second last space shuttle flight ever. And this is a real picture taken up in space of the space shuttle docked to the International Space Station, and this little white box on the top is AMSO2. So AMSO2 was actually designed to measure the sea of charged cosmic ray particles that moves through our galaxy, but it could also measure gamma rays and their polarization. And so in this recent work, we found that if AMSO2 stared at the Perseus galaxy cluster and looked at gamma rays from the Perseus galaxy cluster, then depending on the magnetic fields in the cluster, it could hope to see polarization induced by these kinds of oscillations. Now, at the moment, it's kind of marginal. You have to get lucky with the magnetic field in the cluster for AMSO2 to be able to see a signal from scenarios that aren't already ruled out. But there are ideas for successor experiments to AMSO2 that could do better, and that even for more pessimistic magnetic fields in the cluster would lead to observable polarization. So that I think is just an interesting direction, and an example of how it's not just dark matter annihilation, that gamma rays, as they pass through the universe, can be sensitive to all kinds of new physics, and in particular dark matter. All right, so I'm going to stop there and take questions. Yeah, so just to summarize, gamma rays let us test a wide variety of scenarios for dark matter. There are a lot of examples beyond the ones that I talked about here. With upcoming gamma ray telescopes, we have the potential to test scenarios where dark matter annihilation is what fixed its abundance over pretty much the full mass range where this mechanism works. And we already have examples in the data where we've seen something which could be related to dark matter. It definitely, the galactic center excess, my view is that is definitely something interesting. We're probably going to need to combine with other measurements at other frequencies or in other channels to figure out whether what we see is dark matter or something else, like a population of pulsars in the Milky Way. So I'll stop there and take questions.
Thank you so much, Professor Slatyer. That was a beautiful talk. So many interesting ideas and exciting things to think about. So there were actually quite a few questions. Bernd Huber had quite a few questions. I've suggested that he talk afterwards in private, but I'll take one of his questions, which
Great.
was about Mond-like theories. So
Yeah.
he wants to know to what extent they are ruled out, and so what is the evidence for that at this time?
Yeah, good. So yeah, so I think that if you just looked at the evidence for dark matter from galaxies, so that you just looked at galaxy rotation curves, for example, then at the time where that was most of the evidence that we had, MOND was a lot more popular because it's certainly totally reasonable to say, all right, we see that particles appear to be experiencing gravity that is not what we would expect. Maybe that's coming because there's extra matter we can't see, but maybe it's just coming because of a modification of gravity. Um, the reason it got less popular was because of, I think, two different classes of evidence. One was the cosmological data from the cosmic microwave background. We can we observe now with like really high precision this radiation that was emitted when the universe was only a few 100,000 years old. This was before we had stars, before we had galaxies. The universe was relatively simple then, and it's much easier to model and theoretically predict than what's going on in the cause of galaxies, which require you to know all sorts of complicated stuff, like what has been the history of supernovae going off in that galaxy, which is going to be different from galaxy to galaxy. So the cosmological data is a case where we can make precise theoretical predictions. The data doesn't look at all like you would expect in a universe with no dark matter component, but once you add this 1 degree of freedom for dark matter, you can match the data really, really well over thousands of independent data points. So as far as I know, the scenarios that people work out with modified gravity, the most serious attempts, the way that I've seen them deal with this cosmological data is just to say we insert a new field in our model that behaves just like dark matter for cosmological purposes to get the cosmology right. So I kind of feel that if you need to do that, I mean, it certainly could be that there's some modified gravity going on in addition to that, but I kind of feel that if you need to do that, your model is not actually simpler than just positing dark matter, because to get the cosmology right, you already had to introduce some new field that behaves just like dark matter
Mhm.
for the purpose of cosmology. So that was one. And the other piece of evidence is looking at systems where it seems like the dark matter is getting separated from the visible matter. The bullet cluster is the famous example of this. More recently, there have been studies of galaxies that seem to have lost their dark matter somehow. And those cases are a bit difficult to understand if you're saying that what we think is dark matter is really just modified gravity from the ordinary matter. Like, if that's the case, you should not be able to separate the dark matter from the ordinary matter. You should not be able to separate an object from its gravity. Um, but it makes a lot of sense if it's a distinct matter component and just like occasionally things can happen that pull them apart.
Mhm.
So that's it. So that I think is like that's the reason why most of the field, including me, tends to think that the dark matter hypothesis
Mhm.
like wins the Occam's razor
Yeah.
conflict with modified gravity by a pretty big margin. That said, I am still glad that people are thinking about alternative hypotheses. You know, we have not figured, like, I mean, all our evidence for dark matter comes from gravity. We have not managed to nail this down in the lab yet. Um, it's always good to think about what your next best hypothesis is.
Okay, I'll ask a couple other questions. So Vlad Skylark asks, could dark matter annihilation from high redshift galaxies be an alternative explanation for the cosmic microwave background?
Oh, that's a really cool question. Yeah, so I think the short answer is Yeah, good. So I want to say the short answer is no, but let me think about what kind of assumptions might be going into that. So my short answer, so the zeroth order is that my short answer is no, is that in the standard interpretation of the cosmic microwave background, it was produced, which again, this we can theoretically predict what it should look like, and those theoretical predictions agree really well with the data. The cosmic microwave background we think was produced when the universe was only about 300,000 or 400,000 years old, and that's way before the first galaxies. When we talk about high redshift galaxies, like high redshift galaxies might be when the redshift was 100 million years old. So it's high redshift, but not that high redshift. Um, you can, I Yeah, so it's a good question. One thing that we can look at is like lensing of the cosmic microwave background. So how the cosmic microwave background, how the light in the cosmic microwave background has been bent by traveling through by traveling through the intervening gravitational potential. I so that would certainly be like a cross check on, can you confirm that the cosmic microwave background is really coming from where we think it is? My guess would also be that if it was coming from high redshift galaxies and it just, happened to be at the frequency that would have caused us to infer this 300,000 year emission time, then then my guess is it would be much less uniform than what we see. Like the CMB is uniform to about 1 part in 100,000. Um, yeah, so I mean that's sort of like my set of guesses, that our baseline understanding of the CMB is that it was around for a long time before the first galaxies. But it's a cool idea. And I will also say that like dark matter annihilation in high redshift galaxies definitely would contribute to the cosmic radiation background. So in that sense, it would be maybe not in the possibly in the microwave range, but also possibly at a wide range of other energies. And that's actually a test that you can do as well. Like look for emission from high redshift galaxies, try to correlate that radiation background with high redshift galaxies, and that's a different way that people look for dark matter annihilation and set constraints on dark matter annihilation. It's a
Okay.
great question.
Okay, let's take one last question for the public part of this talk. So Jennifer Rittenhouse West is asking about the distribution. So the gamma ray emission leftover looks compact, but I thought Professor Slatyer said that the dark matter distribution went out quite far from the center of the galaxy.
Yeah, good. So like I assume this is about the galactic center
Yeah,
excess and the
I think so.
plots that I showed there. Let me just try. Yeah, good. So this is partly just a color bar artifact. Um, but yeah, so indeed in these cases, the dark matter distribution that you infer from the gamma ray data is that it has to rise rather steeply towards the dark matter density would have to rise rather steeply towards the center of the galaxy. Roughly, roughly like the density would scale like r to the minus 1.2, where r is the distance from the center of the galaxy. That's pretty consistent with what we expect from simulations. That said, as I said, there's a huge error that like there's a big error bar on that number because the center of the galaxy has a lot of ordinary matter there, not just dark matter, and the behavior of that ordinary matter can change the dark matter distribution in ways that are hard to predict. Um, but yeah, but partly what's going on here is just that the emission is brightest at the center and then fades off fast, and the color bar makes it hard to see the lower emission in the outskirts. But if you do a statistical analysis and ask, is it there? The answer is it's pretty consistently there, at least out to 10 to 15 degrees from the galactic center. And then beyond that, it just becomes small compared to the background, and it's very hard to pick it out. As I said, like the outskirts of the excess are much harder to measure against the backgrounds than the central region, just because the outskirts are much fainter.
All right, well, Professor Slatyer, thank you so much again for a really wonderful talk, actually, and answering the questions so kindly and patiently. If you would like to talk with Professor Slatyer afterwards, please stick around, and I will let you speak. But otherwise, thank you to everybody for coming. Have a great rest of your weekend. Take care.
Well, thanks very much for the good questions, and to FRIB for hosting this,
Absolutely. It's a
and
joy.
for Dean for doing all the work.
Of course. All right, for those who stick around, I'll let you talk. So I will enable speaking. So go ahead, if you're able to talk, go ahead and ask a question.
Yeah.